Okay, so hi everyone. Here my topic is a tracking system design for indoor environments using artificial intelligence. And I'm from Portola High School in California, America. And my advisor is Dr. Yusa from Cal Poly Pomona University. And the presentation outline is background, method, results, discussion, and Q&A session. So background to my research. So it is a common problem that it's hard to identify where the pet is located within the indoor environment. There are existing tools like AirTag, tracking chip, and other GPS collars used for pet tracking. AirTag collar is commonly used for pets, and it is a very popular product, but it was not originally designed for pet tracking, and AirTags can arrow the location of pets down to street and building structure, but they are inadequate as the best for subject in discussion. In addition, AirTag devices often make substantial sounds when they are deployed on the phone to find lost pets, and this could result in further inaccurate results because harsh noises can often scare the animals. Other techniques, such as inserting microchips, have always been used as an identification tool for animals. By inserting an electronic chip with the pet and the owner's identification information, a lost animal with microchip can be easily returned home when found and scanned with a corresponding device. Nevertheless, they are not effective in an active search for animal because the method was intended to mainly keep information about animal and its owner well organized. So here's the overview of my system. The system starts with the beacons, the Bluetooth low energy beacons, and they are sensors that will send out the signals to the receiver or Raspberry Pi with its information, including ID, distance, strings, and time. And then the Raspberry Pi will send the data to the database. We used Google Firebase for this project. And eventually the information will be displayed on the user's interface, and the user will be able to identify where the pet is located. So main tools used for this project includes Bluetooth low energy beacons or BLE beacons, and they are to be worn on pets or other objects for tracking, and will identify itself by sending signals which will be received as received number of signal indicator or RNSI value. And we also use Raspberry Pi for receiving signals from BLE beacons and sending out the data to Firebase. And Firebase and Replit are the main software components. Firebase stores the RNSI values, and the AI system on Replit will perform calibration and calculation for getting the accurate prediction of where the pet is located. And for the Bluetooth low energy beacons, we used RNSI value instead of RSSI value. We collect data regarding the number of signals sent out from beacons to turn that into RNSI value, and we utilize received number of signal indicator or RNSI to track location rather than the commonly used received signal strength indicator, RSSI. Both RNSI and RSSI are measurements of reduced signals. And research has found that RNSI show more significant difference than does RSSI value when the distance of moving object from Raspberry Pi changes. Also, RNSI is more stable in an environment with high signal interference, where many other irrelevant Bluetooth devices may be present. Therefore, I believe this model is uniquely capable of successful implementation with regard to indoor pet tracking. And our Raspberry Pis, we use them to receive the RNSI values for each of the beacon and perform triangulation calculation. And this is a piece of code on Sony from Raspberry Pi. And as you can see, we first get the signals from the beacons, and then we store them and we send them to the Firebase. And on Firebase, we receive RNSI data from Raspberry Pi and store and manage the data in the database. Database is named Raspberry Pi, and the variables under it include receiver 1, receiver 2, and receiver 3. And each of the components is comprised of 3 components of emitter 1, emitter 2, and emitter 3 under them. Raspberry Pi are the receiver and Bluetooth low energy beacons are the emitters. The URL of the database is incorporated into the program in Replit, where the RNSI data are transferred when the program starts calibrating and pinpointing. And here is how the real-time database looks. And the values, they update every minute when we start to run the program. So you can basically get the location of the pet within the most recent minute. And here's a piece of code on Replit. Our main program is on Replit, an online platform that supports users to create coding projects in many different languages. And our main programming language used here is Python. The main steps of getting precise location includes calibrating RNSI value for each room in the house or apartment. Basically, any building will work, and have a pet or an object where the beacon. And then we can start to estimate location, and the location will be shown on the user's interface page. And here on this page of the Replit, we have the calibration function, which is used for when you initially set up the system. You have to get the RNSI value sets for each of the room so they can be used later for calculation. And we also performed 2 experiments to test if our system is accurate enough to be implemented. In the first experiment, we tested if the beacons are consistently working, meaning if they send out signals as they should. And we have shown that the beacons are consistently working and send out signals, and that once 3 beacons are placed together or near each other, they will have similar RNSI values, meaning that all of them are working and they are all working properly. So now we know that the 3 beacons respond with signals, and signals are properly received by Raspberry Pi. And on the left, you can see here this table is the different. We performed 10 trials for the emitters, and all of the 3 emitters send out signals, and they are received in each of the 10 trials. And their values are pretty similar. And they have a low standard deviation, meaning they're very closely clustered to each other. And a lot of times the standard deviation is 0, meaning the 3 beacons or 3 emitters actually have the same RNSI value, showing that they're responding with highly accurate signals, and which will be helpful for our calibration and calculation. And in experiment 2, we started to test if the calculation performed by the AI system to estimate the location is accurate enough to give us the correct results. The results illustrate that the calibration functions well, and the artificial intelligence used for positioning purpose is also very accurate, with 10 out of 10 times or 100% of accuracy. This top picture, it's an example of our calibration for one of the room in the testing location. So there are basically a couple rooms in the testing location, and we named each of them like office, dining room, restroom, living room. They are separated into different areas, and each of the area will assign like a range of surface area, and we get the RNSI values for that area specifically, and then we'll use the existing calibration values to perform the calculation. And after we have done the calibration and gained enough of the values, we start to do testing trials. And this indicates that our algorithm is useful at pinpointing indoor location, and it was a good choice to use RNSI rather than RSI, because RNSI gives an accurate result according to our experiment, with 10 out of 10 times that the object where the beacon were shown were predicted to be in the dining room, which were accurate. So basically, in our work, we designed a system named FindMyPet to make accurate estimates of indoor location of moving objects, primarily pets, using RNSI values interpreted by artificial intelligence. And the main components of the system include BLE beacons, Raspberry Pis, Firebase, Replit, and Kiwi. I haven't discussed Kiwi very much because we are still working on building the mobile application or the web version of it using Kiwi. So Kiwi is basically used for designing apps, and we're still working on that. And the beacons are responsible for sending out signals, and Raspberry Pis are responsible for receiving the signals and convert them into RNSI values. The RNSI values is calculated through artificial intelligence in Raspberry Pi and is sent to Firebase to be stored and managed. Then the RNSI data will be used by the Python program on Replit for calibration and calculating the location. In the end, the users of the system can access the system through a mobile application or desktop user interface, and we perform 2 experiments using established system. Number 1, using 1 Raspberry Pi and 3 beacons to test the eligibility of beacons. And number 2, having a moving pet wearing the beacon to test the accuracy of the current model. And both experiments results indicate that the system is effective and have solved major challenges. And the beacon are working properly, and the system is accurate for indoor tracking. And currently, there are still limitations regarding the system. First, in buildings with multiple electronic devices, RNSI value may be interfered to produce inaccurate results. Common objects such as microwaves can release electronic magnetic radiation and can cause significant flaws in receiving signals from beacons. And besides the microwaves, products such as phones, TVs, and other computers might also interfere with the signals. And the more devices you have, basically more interference you have. And this is a common problem in many households, since that there are multiple electronic devices nowadays, and we'll have to try to solve this problem of high interference so our results could be more accurate. Secondly, the current system is moderately complicated to set up, and if it sold as a product in future in a pet service market, it might cause some difficulties for users, because in order to use the system correctly, the user needs to first record the RNSI value range for each of the room properly and store the value in the administration section of the mobile application. And technical difficulties in setup may occur, and if they fail or have some mistakes when they set up the system might end up not working for them or have very inaccurate results if they recorded the RNSI values wrongly. And lastly, the current system only works with single floor houses because they use 3 Raspberry Pi and trigonometry analysis. For multi-floor houses, the application of the system is currently still largely limited. There are possible future works that could solve the current difficulties. To reduce as much signal interference as possible, we could test a wider range of signal frequencies, and signal frequencies that are significantly different will make it easier for receivers to filter out the untargeted signals. We have in the past experiments, we have figured out that some signal frequencies are received better than others, but there isn't a specific pattern of like if lower frequency or higher frequency is better for the system. So we're still trying to perform more experiments to figure out what's the best signal frequency to set up so we can receive the most accurate results. And the second problem to be solved is the system being hard to set up. In the future, if we plan to sell or manufacture this product, we could offer more straightforward setup instructions and custom service to help. And we could also try to simplify the system, because currently the system contains multiple Raspberry Pis and requires the user to be familiar with how to use the Raspberry Pis and control them through the mobile application. And lastly, by using 4 Raspberry Pi instead of 3, we could achieve pet tracking at multi-floor buildings, and that's something we plan to do in the very near future. With 3 Raspberry Pi, we only track in 1 floor because there's only 3 points, and it only allows a 2D tracking because basically 3 Raspberry Pi will give you 3 values of RNSI, and we could pinpoint the location within a single floor. But with 4 Raspberry Pi, we have 4 RNSI values, and that will allow us to gain the value of to gain 4 RNSI values, and that can give us multi-floor tracking ability, as we know where the pet is positioned within a 3D environment. And so this is basically my presentation, and please ask me any questions you have on my research, or you can also reach out to me through my email, daisygo2005@gmail.com. Thank you, and that's all.